Good day, ladies and gentlemen. This is Notes and Problems on 7.3, Logarithmic Functions and their Graphs. Just a little review. In our last section, we solved simple exponential equations like this. We had 2 to the x equals 8. What in the world is x? Well, we made a simple substitution. In the place of 8, we substituted 2 to the third. And then we made this observation. Since my bases are identical, my two exponents must be equivalent. So x must be equal to 3. No problem. Yeah, but what if we had this instead? 2 to the x equals 9. Since there is no power of 2, I can substitute for 9. I've got a problem. But since 2 to the third is 8, and 9 is a little bit larger than 8, I'm guessing that x would be just a little bit larger than 3. But that does not at all help me in finding exactly what x is. I need a new concept here, something called logarithmic functions. Now here's a concept to keep in mind when you're talking about logarithmic functions. The logarithmic function is the inverse of the exponential function. Inverse. Does that ring a bell? Hopefully. Let's consider an example. Here's something we looked at in 7.1. The exponential function. This one specifically, f of x equals 3 to the x. Another way to say it, y equals 3 to the x. Now you and I found that the best way to graph something like this was pick some strategic x's and find out what the y's are. For instance, if x is -2, 3 to the -2, well, remember that means 1 over 3 to the +2, 1/9. If x is -1, 3 to the -1, that's the same as 1 over 3 to the +1, 1/3. If x is 0, you know what anything to the 0 power is, right? Anything to the 0 power is 1. If x is 1, 3 to the first is 3. If x is 2, 3 squared is 9. Here's what the guy looks like. Here's what the graph of the exponential function looks like. We are looking for inverses of exponential functions. Let me show you a little graphic trick when you are thinking about the inverse of a graph. If I were to draw the line x equals y, and you can imagine what that looks like. Every x and every y is identical. So you got 7, 7, 4, 4, 0, 0, -3, -3. And it makes this line right here. The line that goes 45, a 45-degree angle right through the origin. That's the line x equals y right there. Now, if I want to find the inverse of a graph, all I have to do is either mentally or physically fold this along the line x equals y. So I just make a fold right here, pretty close to it, along the line x equals y. Then the inverse of this particular function, I can find the graph of the inverse by simply folding this along that. So my new function is going to look like that. It's a concept to keep in mind if you're looking for the inverse of a graph. It is the reflection over the line x equals y. There it is, just like that. Another way to do it, and possibly a more strategic way to do it without having graph paper or folding, is simply remember that an inverse switches my x and my y, right? So the inverse of this function is going to have not the 0.29, but the 0.92. not the 0.13, but the 0.31. Not the 0.01, but the 0.10. See how these are each reflections over this line? Not the point -1 1/3, but the 0.1/3 -1. Not the point -2 1/9, but 1/9 -2. And you possibly see what this guy is doing, looking like that. So there's the inverse of this function. There is a picture of the logarithmic function, the inverse of the exponential function. So in general, keep in mind that an exponential function, in general, f of x equal a to the x, looks like this. And it always goes through the point 0, 1. Why? Because if y equals a to the x, and I pick 0 for my x, anything to the 0 power is going to be 1. So the exponential function looks like this in general. That is when my a is greater than 1. Always goes through the point 0, 1. My logarithmic function in general looks like this. Y equal log base a of x is how we're going to write it. Y equals log base a of x. And instead of going through the point 0, 1, it will always go through the point 1, 0. General pictures of the exponential and the logarithmic function. All right. Let me remind you of something we did a while back. You and I said this, that if we had an exponential function, f of x equal a to the x power, I could rewrite that as y equals a to the x. This is an exponential function. Now, if I wanted to find a logarithmic function, I would take the inverse of this. Remember how to find the inverse? We had some steps. Step number 1 was solve it for y. Done. Step number 2, switch my x and my y. In step number 3, solve for y. Here's where I'm going to run into a real problem. How in the world do I solve this guy for y? This is completely different from x equal y to the a power, where I would just take the 8th root and get my y. I've got a real problem solving this guy for y. This is why I need this new concept, the logarithmic function. Here's what we're going to do. We're going to take this guy right here and express it in terms of logarithmic expressions. Now let me remind you of something else. This goes pretty far back. You don't even need to write this down or think about it long, but we had a concept of a fractional exponent. We said, what is that? Oh yeah, it translates to a radical expression. You remember doing that? The base becomes my radicand, the denominator becomes my index, and the numerator becomes my exponent. So anytime I had a fractional exponent, I could express it as a radical expression. Anytime I have a radical expression, I can express it as a fractional exponent. That's what we're going to do with this guy right here. We're going to take a logarithmic function. And just for the sake of generalities, I'm going to express my logarithmic function as f of x equal log base a of x. Another way to write that is y equals log base a of x. What in the world does that mean? Well, just like in this case, I can re-express this very confusing statement into something I'm familiar with. I can change a logarithmic equation into an exponential equation like this. First of all, this is log base a. First thing, a is going to be my base. A to what power? To the y power is going to equal what? It's going to equal x. So if you have a logarithmic equation, you can translate that to an exponential equation in exactly this way. Log base a, the base stays the base. This is my exponent. This is my solution. So a to the y equals x is the same as saying log base a of x equals y. Let's practice changing exponential expressions to logarithmic and logarithmic to exponential. Like this. Log base 3 of 9 equals 2. Kind of confusing until I put it in exponential form. All this is saying is that 3 raised to the second power is 9. Makes perfect sense. Try another one. Log base 8 of 512 equals 3. Again, if I were asked to express this in exponential form, I'd say no problem. 8 to the third power equals 512. One more. Y equal log base 2 of x. I'm not sure what x and y are. Don't have to be. I can still express it as, and notice this, the log part is on the right now. It used to be over here, but it's still the same thing. This is still my base. This is still my exponent. 2 to the y power equals x. I can take a logarithmic expression and express it in terms of an exponent. Likewise, I can go in the opposite direction. 5 to the fourth equal 625. Can you put that into a logarithmic expression? Okay, try this. And notice when we had an exponential expression, this is my base. So log base, whatever the base is going to be my base of 625. And this solution over here is the exponent. Here's another way to think of a logarithmic expression. It's simply saying this. A logarithm is an exponent. So think about this. If you see log base 5 of 625 equal 4, here's what you're saying. The exponent that I raise 5 to give 625 is 4. The exponent that I raise 5 to, to give me 625 is 4. 5 to the fourth power is 625. The exponent that I raise 5 to get 625 is 4. That's another way to think of what a logarithmic expression is saying. All right. With that in mind, here are some frequently encountered logs. Hey, we had log base 2, we had log base 5, we had log base 7, but those are unusual. These are the guys that show up often. Log base 10 and log base E. Now they show up so frequently that we have abbreviations for them. Instead of saying log base 10, I simply say log. And since this is the most common expression of a logarithm, this is called the common log. Log base 10 is the common log. It's so common that we simply use log itself. Just like, remember, square root of x, we typically don't put that. We just say square root of x. Why? Because it shows up so frequently. Common log is log base 10. So let's look at these guys. Log base 10 of 100 would probably be written without the base, log of 100. And if we were trying to find out what log of 100 is, we could use our transformation of a logarithmic expression into an exponential expression. If I had log base 10 of 100 equals x, I could simply say, well, this is saying 10 to what power equals 100. And we do here what we did in 7.1. In the place of 10, we would put, in the place of 100, we would put 10 squared. So 10 to the x equal 10 squared. Aha, x must be 2. Or, and here's where your scientific calculator comes in handy, log, the common log, right there, log, and natural log, represented as ln, both show up on your calculator. So if I wanted to find the log base 10, or just log of 100, I would hit log, put in 100 equals, and it tells me, what do you know, exactly what I found out. 2 is the common log of 100. So when you have log base 10, or in a minute, log base E, you can use your calculators. Hey, this is not going to come out even, is it? Because 45 is not 10 to some power. So let's find out what log base 10, or log of 45, is. And we would typically write that as log of 45. And we use our calculators. Log of 45 is, and rounding to 2 decimal places, I get 1.65. So this is approximately equal to 1.65. All right, that's the common log, and you have a function key on your calculator to do log base 10. The other frequently encountered log is log base E. This is represented on your calculator as ln. And since this base, this value, shows up so much in nature, this is called the natural log. I'll explain that in just a second. If you have, for instance, a petri dish with a virus on it, hey, there's a timely illustration. If you have a petri dish with a virus or a bacteria on it and you want to see how it grows with a function that involves this number, E. It shows up constantly. If you want to see how a population of a country grows, it will be a function and it will involve this number, E. This is an irrational number, just like pi is an irrational number. It's approximately 2.71 something. That's given to you a little bit later on. In fact, if I want to find out what it is, I've got an e to the x. I'm going to put e to the first power to see what e is. It is 2.7183. That's approximately what e is. So if I see log base e of 25, I would typically write that as ln of 25. And once again, I would use my calculator. ln of 25 equals, rounding to 2 decimal places, 3.22. So that's approximately equal to 3.22. Again, log base e of 100, you would more likely see that represented as natural log of 100. Again, I would use my calculator. Natural log 100 equals, I get 4.61. It's approximately equal to 4.61. So these are frequently encountered logs, and you need to be familiar with them. Log base 10, abbreviated log. Log base e, abbreviated ln. All right, a couple of logarithmic concepts that you need to keep in mind. And we're going to get into these in more detail in our next week's lessons. But this is the basic concepts involving log that you need to keep in mind. Here's the first one. Log base anything of 1 is always going to be 0. Why is that? Well, let's translate this to exponential form. A to the 0 power equals 1. Oh yeah, makes sense. Anything to the 0 power is going to be 1. So I don't care if you have log base 27 of 1. What's that going to be? That's going to be 0. Log base 13.6 of 1. What's that going to be? That's going to be 0. Log base e of 1. What's that going to be? That's going to be 0. Log base 10 of 1. What's that going to be? That's going to be 0. Log base anything of 1 is going to be 0. Good thing to keep in mind. Here's the second thing to keep in mind. Log base a of a equals 1. And when I put this in exponential form, it makes sense. A to the first power equals a. Oh yeah. So if I have log base 7 of 7, that's simply going to be 1. Log base 10 of 10, that's simply going to be 1. Log base e of e, that's simply going to be 1. So if my base and my value are identical, my answer to the logarithmic evaluation is 1. Here's the last one. Log base a of a to the x, that's just going to be x. Let's see why that works. A to the x equals a to the x. Hey, it makes sense. So this value is almost redundancy. A to the x equals a to the x. Let's see what something like this looks like. Log base 3 of 3 to the 5th power. What do you think that's going to be? 3, it's going to be 5. How about this one? Log base 2.1, log base 2.1, oh my gosh, of 2.1 to the 10th power, same, simply going to be 10. How about this one? Log base 10 of 10 to the 4th power, remember the 10 is there, understood, my bases are identical. It's just going to be 4. And look at this one. Log base e of e to the 21st power is just 21. So if these two are identical, my solution is simply going to be my exponent. We're going to refer to this a little later on, working our problems. All right, here's our first problem for Hawks. It says identify the graph that represents h of x equal log base 9, that's a 9, not an a, log base 9 of x minus 1. Now, the best way to do this is just, you know how Hawks does it. It's going to give me 4 graphs, and I got to pick the one that represents this guy. The best way to do this is to find a couple of illustrative points on this particular function. And the first thing I'm going to do is remind myself that h of x is the same as y. And I'm going to think, hey, what would it be real easy to find? Log base 9 of what? Well, I know that log base 9 of 1 is going to be 0, right? So if I can take log base 9 of 1, it's going to give me 0. That means I want this thing in parentheses to be 1. What would x have to be to make this 1? Well, if I choose x for 2, 2 minus 1 is 1. Log base 9 of 1. Log base 9 of 1 is going to be 0. So if I choose 2 for x, I would get y equals log base 9 of 2 minus 1. That's log base 9 of 1. Log base anything of 1 is going to be 0. All right, so I got a point. And when I look at my graphs, I see, hey, what do you know? At least 2 of them have this point. So 1 point is not going to be enough. I need another point. Hey, here's another concept. Log base anything of itself is going to give me 1. So if I can do log base 9 of 9, if this would be 9, then I would get 1. So what would x have to be to make my parentheses 9? Well, 10 minus 1 gives me 9. So if I pick x to be 10, choose x equal 10, I get y equals log base 9 of 10 minus 1. That's log base 9 of 9. And my principles tell me that log base 9 of 9 is going to be 1. So it also goes to the point 10, 1. So find the graph that has the points 2, 0 and 10, 1, and you've got your solution. And there's only one graph like that. All right, let's evaluate this guy. Let's evaluate log base 10. There's no visible base there, so it's log base 10 of 1,000 without using a calculator. So let me remind myself that log base 10 can be written this way as well. And that's going to help me because I can now express this logarithmic expression in exponential form. And I'm going to write it this way. Log base 10 of 1,000 equals what? It equals x. Let's solve it. Let's put this equation in exponential form. 10 to the x power equals 1,000. Now this is just like our 7-1 problems. If I can express 1,000 as 10 to some power, I'll be finished. And I can pretty easily. 10 to the x is 1,000, but 1,000 is the same as 10 to the third. Hey, I have identical bases. That means my two exponents must be equivalent. So in this case, x is 3. All right, let's try some more. It says, use the property of logarithms to solve for x. Well, this is obviously a logarithmic equation that I can translate to exponential form. This is kind of confusing, but it's very solvable once I realize that I can express it in exponential form. 2 to the fourth, refer back to your example of how to express, how to change a logarithmic equation into an exponential one. 2 to the fourth equals 7x. Well, I know what 2 to the fourth is. 2 times 2, that's 16. I'm one step away. Divide by 7, and I got it. X is 16 over 7. That wasn't bad. Just translated the logarithmic equation into an exponential one. Same thing here. Evaluate without using a calculator. So I'm going to evaluate this. Log 1/3 to the 9th equals x. I'm going to express it like that. And I'm going to change this to an exponential form. 1/3 to the xth power equals 9. This looks again strangely like those problems we worked on 7-1. If I can express both of these sides as something, the same thing to a power, then I can equate my exponents. And you probably guess we're going to look to express the common with a common base of 3. This one's easy. This is 3 squared. But 1/3 to the x power is a little bit more challenging. Let's express it as 1/3 to the 1 to the x power. That's the same, right? 3 is the same as 3 to the first. And let's remind ourselves that I can move a factor to the other part of the fraction if I change the sign of my exponent. So 1/3 to the 1 is the same as 3 to the -1. So in the place of 1/3 to the first, I put 3 to the -1. It's still to the x power. Don't forget that x power. Look here, I got powers to a power. I'm going to multiply. -1 times x is -x. Identical bases, that means my exponents must be equivalent. So -x equals 2. Multiplying both sides or dividing both sides by -1, I get x is -2. Is that okay? All right. This says evaluate without using a calculator. And believe it or not, I'm going to be using one of these basic properties of logarithms. This is very confusing. Until I remember that a radical expression may be expressed as a fractional exponent. So I get natural log of, there's my base, e, here's my fraction, 3/6. And I got two things to think about here. Number one, ln, natural log, I can say is log base e. I'm going to say it this way just because it makes my property of exponents clear. Log base e of e to the, I'm going to go ahead and reduce this, 1/2. Look at your properties of logarithms. Log base e of e to some power. Log base e of e to some power. I'm going to apply this. It's just going to be whatever that power is. Log base e of e to the 1/2 is just 1/2. I have evaluated that without using a calculator. I use the properties of logarithms. When my base and my base are identical, my solution is just the exponent. All right. Check out the next one. This one is easy. It says simply write as an exponential expression. They don't want you to simplify anything. They just want to rewrite this logarithmic expression in exponential form. Look at your example. There's my base. There's my power equals that. And I'm finished. That was easy. That's all they want us to do. That to that power equals that. All right, solve the logarithmic equation. I'm going to do, this is very confusing in the way it's looking here, but if I express it in exponential form, it's going to become much more solvable. So I'm going to translate this into its exponential equivalent. 7 to the second power equals whatever this is. Well, this is going to be pretty easy. 7 squared is 49. Add 5. Divide 2, and I got it. That wasn't any problem at all. It wasn't a problem at all when after I translated it to an exponential expression. This is confusing looking. This is very workable. All right, here's another one of the identify the graph that represents. I can, if I want to, start thinking about the transformation of graphs. Like here's a vertical shift of up 1, right? Yeah, that's going to possibly help some of you. What I would suggest is find 2 illustrative points. So I'm going to find some illustrative points. And the first thing I'm going to remind myself of is that I can re-express g of x as y is log base 2 of x, whatever that is, plus 1. Keep in mind, I have to evaluate this before I add the 1. All right, let's find some points. First of all, I'm reminded that log base anything of 1 is easy to find. It's 0. So I'm going to let my x be 1. So y is log base 2 of 1 plus 1. Log base 2 of 1, log base anything of 1 is going to be 0. So log base 2 of 1 is 0 plus 1. That's 1. So I get the point 1, 1. Well, that was easy. I'm also reminded that log base anything of itself is 1. So log base 2 of 2 is going to give me an easy answer as well. So I'm going to pick 2 for x. Y is going to be log base 2 of 2 plus 1. But I know that log base 2 of 2 is just going to be 1. So that's 1 plus 1, that's 2. Got another point, 2, 2. Let's do one more. Let's pick a power of 2, like a very simple power of 2, like 4. y is log base 2 of 4 plus 1. Hey, here's where, believe it or not, I can use this third property of logarithms. If I can express this 4 as 2 to some power, then I will be well on my way. So log base 2 of 4 is 2 squared. Hey, look at this guy. Log base 2 of 2 to the second. Log base 2 of 2 to the second is just 2. It's just whatever that exponent is. When my bases are identical, it simplifies to the exponent. This is just 2. Plus 1 is 3. So I've got 3 points, and believe me, that's enough to find where to identify the graph that represents this particular logarithmic function. Hey, see how handy these guys are coming in? All right. Here's a doozy. It says identify the graph that describes this guy. 5 minus log base 1/4 of x plus 1. Again, if you are skilled in transformations, notice we have a horizontal shift, 1 to the left. We have a negative in front of the whole function. That means a reflection of the x-axis. We have an addition of 5. That means a vertical shift up. You can use transformations, but I would suggest find a few illustrative points. Pick some convenient x's and find out what y is. Now, a couple of things I'm going to do. One is, of course, I'm going to change this out for y. The second thing I'm going to do is put the 5 at the end. Because those of you who will be thinking in terms of transformations, this needs to show up at the end because it is a vertical shift, right? Up 5, to the left 1, reflection over the x-axis. And if you do your transformations, be sure and do them in the appropriate order. Horizontal shift, reflection, vertical shift. All right, but my suggestion is, that's a little confusing for me, so my suggestion is let's find a couple of illustrative points. So let's find some x's and y's. All right, keep our properties in mind. If I have log anything of 1, that's going to be simple. So I'd like this to be log of anything of 1. What would my x have to be to make this parentheses 1? Well, 0 plus 1 is 1. So I'm going to choose 0 for x. So that means my y is going to be the negative log base 1/4 of 0 plus 1 plus 5. This is log of anything of 1, that's just 0. The negative of that is negative 0 plus 5, that's 5. So I've got a point, 0, 5. Check your graphs and you'll find that 3 out of the 4 have the point 0, 5. Doesn't help me that much. I need another point. I'd like to find out what log, when my base is 1/4, what log 1/4 of 1/4, I'd like to have that. Log base 1/4 of 1/4 will give me 1. That's a nice, easy concept. So if I can make what I'm looking at the same as my base, I'll find out that that's 1. So I'd like this to be log base 1/4 of 1/4. Here's the question. what would x have to be to make this parentheses equal to 1/4? That's more confusing. Probably can't do that in your head. So let's just say x plus 1 has to equal 1/4 and solve that for x. Minus 1, minus 1. That's x is 1/4 minus 1. That's the same as 1/4 minus 4/4, right? 1/4 minus 4/4 is negative 3/4. That's not an obvious answer. But look here. Negative 3/4 plus 1 gives me 1/4. Log base 1/4 of 1/4. There's my 1. So I'm going to let my x be negative 3/4. Here's what happens. I get negative log 1/4 of negative 3/4 plus 1, and then plus 5. What I get is negative log of 1/4, log base 1/4 of 1/4 plus 5. Now remember, when my base and my number are identical, log base a of a, log base 1/4 of 1/4, that's just equal to 1. So this is 1. Make it negative. I get negative 1 plus 5. I get 4. So I have 2 points, 0, 5, and negative 3/4, 4. And believe me, there's only one graph that has those 2 points, and that's the one you choose. All right, just about finished. It says, solve the following logarithmic equation. ln of e to the x equal 22.7. Well, believe it or not, this is an application of the third property of logarithms, where my base and my base are identical. I can rethink natural log as log base e. It's the same thing. Log base e of e to the x equals 22.7. I'm wondering what x is. This is exactly this principle. Log base e of e to a power is just the power. Log base e of e to a power is just the power. So x is 22.7. Hey, another way to think of it, if you translated this into a exponential equation, I would say e to the 22.7 is the same as e to the x. Look at there. Identical bases, my exponents must be equivalent. Either way, you're going to get x is 22.7. Next, the last one. Solve round to 2 decimal places. And here's my approximation for e, 2.7183. If you ever forget that, you can go to your calculator and just use your function key e to the x and put in e to the first, and it will give you 2.7183, etc. So just find out what e to the first is on your calculator, so you're never far from knowing what e is. All right, this is what they want us to solve. And I'm going to go ahead and re-express natural log as log base e. Why? Because I'm going to translate this logarithmic equation into an exponential equation. Here we go. E to the third power equals 2x plus 5. Still confusing until I remind myself that e is just, hey, it's just a number. So I'm going to put 2.7183 to the third power into my calculator, And I'm going to get equals 2x plus 5. Don't round yet. Keep it in its full expression. I'm going to subtract 5 from both sides. I'm going to get 15.08593974. I'm going to divide both sides by 2 and round my answer to 2 decimal places. And I'm going to get x is approximately equal to 7.54. So the only thing we had to remember here is natural log is the same as log base e. E the third power can be evaluated with your calculator without much problem. Subtract 5, divide 2, and I got it. All right, last one. Solve the following equation, reduce any fractions. Again, I have a logarithmic equation. I'm going to translate that to an exponential equation, and here we go. 81 to the 3/4 power equals x. 81 to the 3/4 power equals x. Hey, this is like our 8 to the 2/3 example, right? I know what to do with this guy. This simply means, there's my index, the 4th root Now, I could cube the 81 in here, but in that case, I'd be looking for the 4th root of a really ginormous number, and I'm not too fond of doing that. But this case is very simple. The 4th root of 81, look at your chart. You'll find that 3 to the 4th power is 81. The 4th root of 81 is 3. 3 to the 3rd, that's on your chart. It's also on your calculator. X is 27. All right, I will put these notes, post these notes on Quickly Content. I will also do my best to upload this video for your instruction. And good luck. You have these 2 sections, 7.1 and 7.3, due by Sunday at midnight.